Hi, I'm John Michael Hands, VP of Storage at Chia Network. I'm going to give a presentation today called Proofs of Space, Storage to Secure the Blockchain. This is an overview about how Chia utilizes storage in the proof of space and time consensus mechanism. This presentation was for Flash Memory Summit 2022. The audience was primarily people in the storage industry, so it's basically a lot of introduction about cryptocurrency, why cryptocurrency is good, how do we use storage in Chia, and then a lot about farming and plotting. Introduction to cryptocurrency. So cryptocurrencies are inclusive and permissionless networks. We like to say controlling your wealth is a human right. Uh, I know we have it lucky in the US. Obviously, we can go to the bank and I use my credit card every day and I'm pretty sure it's going to go through and that the government's not going to one day just seize all my money. But we have to remember that not all countries are like this and controlling your wealth is a human right and we need to make it more inclusive. And you can only do that through a permissionless network. And the point of a blockchain is to be censorship resistant. We want it to be difficult or impossible to block participants. So anybody can send any transaction whenever they like. Now, this has obvious implications. People sometimes confuse this with blockchains being bad because they say, oh, well, can't criminals and all kinds of bad people just do lots of transactions and things that are censorship resistant as well? And that is true. But this is no different than freedom of speech, where you have a rule that is generally good. People are going to say things that you don't agree with, but having freedom of speech is better than not having it. So this is exactly the same way that permissionless networks work. The idea that we have an independent monetary policy, this idea of trusting math, not people, is that all the rules in the blockchain are written down in code. And this consensus mechanism, the way that people agree on the blockchain rules, can't just change mid-time. The way that these change are through these things process called forks. And a majority of the people in the network have to agree on a certain change before it goes through. So these are governed by these consensus mechanisms, but it's trusting the actual code, not the people. You can write unstoppable applications. So a program developed for and run on a secure blockchain can never be changed or stopped. So again, when you have a smart contract in Chia, we use smart coins. This is programmed in the blockchain. In Chia Smart Coin, the coin has certain rules that are programmed into it, and you literally cannot spend the coin unless it meets all those conditions. And these can't just be arbitrarily broken. These are actually programmed into the chain and enforced on chain through all the validators in Chia. We call these people farmers through the network. The best thing about cryptocurrencies, one of the best things, are they are global standards, right? They are collaboration of fully open source and available for free. Everything Chia has released has been open source, and we have participants from all around the world. If you look at our Chia network graph, which shows a view of all the nodes across the world, it's not shocking that we have participants from every area of the world. Um, we like to joke that we have 2,000 nodes in Ukraine. This is one of the full nodes counts from if you look at the total blockchain count. So you can just see that there's a huge amount of decentralization in the network, but this isn't limited to a single country. This is part of what also makes it a unstoppable blockchain and permissionless network is that if, for instance, one big country, even if it's a large participant, like today in Chia, there's lots of folks in US and China, if these governments decide to try to censor transactions or shut off the network or block ISPs from accessing cryptocurrencies, this will not take down the network. It has to take coordination from every government on earth in every single country to take down the network. And that's not possible, of course. And we say secure and decentralized. Decentralization in Chia matters. We view decentralization in a few ways. One is this obviously that you have lots of different participants in the network, and there's a way to describe this. It's called the Nakamoto coefficient, or the amount of participants it would take to do a 51% attack or takeover attack in the network. And we have a very high Nakamoto coefficient because the incentives for Chia are for farming, right? So people that are joining the network, they generally put up their node to the network in an ability to earn reward. So they get compensated for putting their storage space on the network. But this idea that you have this massive decentralization comes from the good incentives of blockchain. So that participants get rewarded for securing the network, and that incentivizes more people to put up nodes all around the earth. And this actually makes it very decentralized and hard to attack. And this is when we say secure and decentralized. Secure, one part of it is just in Chia we have a physical asset, which is capex. So in Chia mostly today it's hard drives that secure the network. This is important versus something like proof of stake, uh, because in proof of stake these assets, this is what makes it a decentralized and permissionless system called Nakamoto consensus. This is truly random block time and distribution in Chia, where participants can join the network and they can leave the network whenever they want. In a proof of stake system, you may have to stake your coins and you may be locked up for a certain period of time. In Nakamoto consensus in Chia, you can join the system and you can leave the system. You can put your hard drives and storage on the network whenever you want. You can take it off whenever you want. There's no penalty to do that. Um, Programmable money, the most important thing about cryptocurrency isn't just that it's secure. People like to think of Bitcoin as a store of value. This is really awesome part about cryptocurrency, but you really want to think a lot bigger than that, which is programmable money. In Chia, we have, well, I mentioned what we call smart coins, but you can program anything that you want into the coins directly themselves. So anything that you can think of, one of the sayings I like about this is what rules govern this money. And we have lots of interesting features like wallet, clawback, and rate limited wallets, like a certain amount can only be taken out per day. You can have time locks on it, like a certain time restriction of when you can withdraw assets. You can make up all these interesting rules around the money. And the idea is that cryptocurrency should be easier to use than cash and harder to steal. And through smart contracts and smart platforms, you can make this an actual reality. Chia is a sustainable and secure blockchain. Obviously, the most novel thing about Chia is that it uses storage space. We call this proof of space and time. But the idea behind using storage was, one, is that it's a commodity asset. So everybody has storage. It's widely available. It's available in every country. It's a highly competitive market with multiple global participants, and it's vastly underutilized. So IDC has this report called Age of the Data Sphere, which they have basically estimate the amount of data created in the world. And then the sister report to that is Age of the Storage Sphere. And these reports basically say how much storage are there in the world how much data in the world is being stored versus created. And one of the interesting metrics they have is this thing called underutilized space. So in 2022, the 9.4 zettabytes of estimated storage on Earth, that's all the data being stored on Earth, 3.1 zettabytes of that data is underutilized or not being used. So this is a tremendous opportunity to take that underutilized asset and use it to secure the blockchain. In Bitcoin, the original idea behind Bitcoin was one CPU, one vote. Obviously, that didn't turn out because people made ASICs and hardware acceleration for SHA-256. In storage, a bit is a bit. And so this is really a nice way to democratize this commodity. And you can't make a ASIC for storage that's faster because in Chia you're not getting rewarded for the latency and speed of the storage beyond what is actually suitable for the network. So for instance, if you have an SSD space, you're not getting rewarded for that being faster than a hard drive. So a gigabyte is a gigabyte, a terabyte is a terabyte, and this is a way to kind of level the playing field for a commodity asset. Also, the most important thing about storage is it's power efficient. Storage is called non-volatile memory, which means that the state of the memory in storage is retained after a power loss or a power off. And obviously, you know this when you turn off your hard drive and turn it back on, or turn off your SSD and turn it back on, your data is still there. This is really important for Chia because we've designed the protocol for the drives to be mostly idle so that future enhancements, especially with SSDs, can basically do this farming activity at near zero power. We like to think of our blockchain as decentralized and inclusive. We actually believe that Chia is the most decentralized blockchain in the world. Our blockchain node count fluctuates between 100 and 2,000 nodes for over the last 6 months. I think as of today, it's about 120,000 nodes, which would make it, as far as running full nodes, the most decentralized blockchain in the world. Why is it so decentralized? Well, it's very easy to run a node. This isn't magic. Brian likes to say, this is good engineering. We've designed the state transactions and validation of the blocks to be very lightweight, and the actual act of farming and all this has been designed to be very low energy and low overhead, so people can run a farmer on something as low as a Raspberry Pi. And this is why we've been able to scale to hundreds of thousands of nodes. The last thing of why we're sustainable is that Chia incentivizes the circular economy. So in the Chia protocol, the drives are not designed to store user data. This is different than storage or Filecoin or other storage-based cryptocurrencies that are actually storing user data and taking an asset or a token in exchange for that. In Chia, the storage is just used for the consensus mechanism. So no real user data is stored, it's just these cryptographic plot files. And so this makes it a perfect opportunity for use storage. You don't need a high amount of data durability. You don't need a lot of reliability. If a drive fails, you can replot. You can use all plots are fungible. So this whole idea of getting used storage. Well, it turns out that most of the drives today on Earth get shredded at the end of first use because of perception of security concerns. So we're working with the industry to try to change this practice. And previously, they didn't think that there was any massive use case for used drives, drives that were 5 to 6 years old that were leaving hyperscale data centers. And now we've offered a tremendous opportunity and use case for used storage through Chia. One of the earliest blog posts I wrote for Chia was a blog post called Farming versus Mining. And of course, we have these new terminology of farming, and we call it farming because it is actually low energy use. Mining, the actual term mining comes from this continued use of resources to basically extract value. And that's totally a great word for the process of cryptocurrency mining because you're just burning through all this energy trying to find blocks. In farming, you do the work upfront once. You store these cryptographic hashes on plot files and hard drives, and then challenges come in from the network. In our network, they come from these things called time lords, which use a verifiable delay function. We'll talk a little bit about that. Basically, the farmer checks their files on the hard drives to see if they have any winning proofs. If they find a winning proof, then they broadcast that to the network to find the next block on the blockchain. And of course, these farmers get rewarded for their incentives for putting their storage space in the network. Today, the reward is 2 Chia per block. In the future, every 3 years, that half. So in 3 years from our mainnet launch, it'll go down to 1 Chia as a reward per block. But the whole idea of farming is that it's energy efficient, and the drives basically just sit there mostly idle. Now, obviously, Chia had to invent some new technology. We use these things called proofs of space. So, proof of space means exactly that. You're proving that you're storing a certain amount of data on the network. And so, how does a farmer do that? Well, these proofs need to be quickly and easily verifiable. You don't want to have to read all the data back every time a network challenge comes in because then that makes it extremely bandwidth intensive. And that then again, you're just like proof of work because you're using a lot of energy. So we needed to make these proofs easily and quickly verifiable, which will be part of the topic of today's talk. And the network needs to be resistant to attacks. And that is part of what has been designed into the proof of space construction for Chia is a way to make it very hard to game the system. And we'll show you these. We use these things called plotting tables in our plot files that make it exponentially harder to attack these plot files. Proofs of time are these things called verifiable delay functions. In Chia, a verifiable delay function is a function that can't be parallelized. It has a canonical output. It's easily verifiable, and that a real amount of time was spent doing these computations. In Chia, they perform these squaring computations of class groups with binary quadratic forms. I know this sounds like magic math, but really, idea is the proof of space is in there to prevent these things called grinding attacks, where you can try to a farmer, say for instance, that has a lot of space, can try to predict what the next block would be and rewrite history by looking at lots of different versions of history. If you have a source of time, in this case, time meaning computations or iterations of our verifiable delay function, and that's basically preventing many of these attacks. So the combination of these two things are what is called proof of space and time. And of the weight of our blockchain, again, in Nakamoto consensus, you can basically trust a blockchain that has the longest weight. You don't have to trust any verified third parties. You just look at a bunch of peers in a peer-to-peer network. You ask all the peers who has the longest blockchain, and from there you can basically trust one with the one with the longest weight. And remember, in Chia, the weight is the space times time. Graham likes to joke that it's generally not a good practice to have invent new math here on your product roadmap. In Chia, in fact, they had to do it 2 times in the history. One with our plotting format to make the plot secure for the proofs of space, and this was originally described in the Beyond Hellman time memory trade-offs with applications of proofs of space paper. Now, this paper describes how the proofs of space construction work with the plotting tables. The other was for this VDF, which is this binary quadratic forms, and these two combinations of new math, the class groups and binary quadratic forms, is brand new math that in this VDF. The Chia is the first production blockchain to basically use this VDF. In Chia network, we have these things called this process called plotting, which is the initialization phase. This is where you create the proofs of space into something called a plot file, and this requires a one-time use and upfront use of compute resources. I mentioned so that the idea is that it's harder to do this first process because we don't want Chia to turn into proof of work. So we want some work up front once, and then you write that to disk. And the plotting has to be not too easy, but not, we don't want it too hard either. So you have to have this very, very interesting sweet spot where you've tried, it takes, a few minutes to say 30 minutes to make a plot file. You don't want it to be able to be created in just seconds because then it would just turn into proof of work. The harvester in Chia is actually these things that are connected to the farmer, and the harvester is the actual code that basically are these lightweight machines that basically look at scan the plot files for these proofs. And the idea, and you can see in this diagram, you can have multiple harvesters attached to a single farmer, and this makes it so you don't have to do a lot of the redundant things that you're doing as a farmer. And the farmers are the people that are competing to make proofs of space. A farmer are going to basically take these proofs that they get from the harvesters, and they're looking at these challenge requirements. The farmer is going to get the challenge requirements or the signage points from the full nodes, and then they're going to pass those to the harvesters. The harvesters are going to check the plots and then pass them back to the farmer. The pool protocol in Chia is a way to basically, and it's very interesting in Chia, this is very novel, where in Chia, the people in the pool protocol actually make the blocks themselves. So the pool is not making the blocks, the farmers are making the blocks, but the way that the pool protocol works is that the rewards go to the pool. 7/8 of the reward today go to the pool, and then the farmer gets to retain 1/8 of the reward when they win a block. But this is a very clever way to do pooling that is built into the protocol itself so that you don't have to have a pool with a ton of hash rate or power that controls the network. The last thing, of course, is this full node, and a full node in a blockchain is this is the peer-to-peer part of a blockchain where the nodes are communicating with each other to propagate blocks, to do transactions, to look at proofs between peers. The full nodes are the ones that have to maintain sync of the blockchain. So in Chia, the full node, basically you have this blockchain weight and you're adding blocks to the blockchain. You're validating the transactions that are coming in. And then the full nodes talk to each other to make sure that the weight and the peak of the blockchain is the same across different nodes. In Chia, you basically create the files on your plotter and then transfer them to your farmer or obviously harvesters, which are generally stored on HDDs. So you can see here's a picture of the GUI. You can select your K value. In Chia, K equals 32 is the default value. We don't allow plots under K equals 32 on the network. That's one of these things you can tune in your consensus. And you can see here, this is just a screenshot of a hard drive with a bunch of plot files. These plot files, they just look like regular files, but they are big. A plot file is 108.8 gigabytes or 101.3 GIB. And you can see these plots are actually made up of a bunch of different tables. Now, a user doesn't know that. A user just sees a plot, it has its plot ID, and the data was created, and it's a dot plot at the end. Now, internally to these plots, they have these plotting tables, and this is one of the key insights in the Chia Proof of Space, which made it resistant to attacks. Other people had tried proofs of space previously. In like 2015, I think there was a couple that tried proofs of space, but they didn't understand this process of this thing called a Hellman attack, which is basically a Hellman attack does a time-space trade-off. You can do these certain inverting of functions, but basically you can compress the file by putting in more compute up front. And we want to make that very, very challenging, if not impossible, in Chia by having 7 tables. So the reason why you have 7 tables are the tables are nested, and you have back pointers from the original entries in the first table, and it gets exponentially harder to do these Hellman attacks as you traverse down the tables. So in Chia, you can do Hellman attacks, but it gets exponentially harder and to the point where it just takes infinite compute at some point. And so this makes it very hard to game the system so that people don't have an unfair competitive advantage in this making these plots. And again, the other thing is that I have to be able to be quickly be able to retrieve proofs. And so the way it works, you can see in this red, a challenge comes in, you can traverse the tables back to table 1 in the entries, and you can read this full proof of space, which today is 64 entries. And this plot size, as I mentioned, is determined by this K value, this K. And so in these tables, you have 2 to the K entries per table. I mentioned a common value in Chia is K equals 32. Make no mistake, plotting is a write-intensive workload. That process I just described, you have to basically write out a lot of data on disk. You have to sort it and compress it. And today, each plot, if you're doing this on disk, takes about 1.43 terabytes of disk writes. Now, like lots of enterprise workloads, you can basically throw DRAM at it and reduce the amount of disk writes. And today, if you throw about 110 gigabytes of DRAM, about 100 gigabytes of DRAM, you can reduce the writes by 70 to 75%. And on this one I'm stating with Mad Max, Chia Plotter, it's 72% reduction with 110 gigabytes of DRAM. Now, if you do this process completely in memory today, it takes 416 gigabytes of DRAM. We have a plotter called BladeBit that does this sorting completely in memory, but it can be theoretically done with lower amount of DRAM. It's just much harder to code. But we have this Chia Proof of Space construction document that basically describes this process and the algorithms that go through in the plotting. Chia plotting generally has a few distinct phases. This first phase, called forward propagation, was you're writing on all the data in the tables. Now, technically, would be all you need to farm, but this is not the most space compressed version of a plot. When you write out after just phase one, you have generally a couple hundred gigabytes of data. And so you have to go through in phase two and prune all these entries and go back, scan and traverse all the tables and remove the ones that are unused. And then in phase three, you're actually doing this algorithmic compression. This is not a standard compression algorithm. This is algorithmic line point type compression, where you're going back through the plot and putting these in the deltas and stub format. You're just reducing the amount of space that this plot, the actual organization of all the proofs in the plot file are represented on disk. So again, don't think of this like regular compression. It's algorithmic compression. And the last point is this checkpointing phase, where you're basically making it easy to do these quick and verifiable lookups. There are 4 current Chia plotters that are being used. One is the Chia POS, which is a Chia Proof of Space. This was our original design for the Chia plotter. This was our reference plotter. We had initially multi-threaded phase 1, but the rest of the phases were not multi-threaded. So it does support any case size value, and it's very slow. Nobody in production is really using this today unless they want to do these boutique, like very high K value plots. Mad Max plotter was developed in, I believe, July of 2021, a few months after we launched mainnet, and this was a pipeline version of the plotter. So they used some of the code from Chia POS, but pipelined it and multi-threaded it. And the way this looks is it looks very random IO to disk. You have a certain amount of threads, and each thread basically is producing some of these buckets. So you take some of these tables that I just mentioned in these plotting tables, you break those tables into buckets, and then you read those buckets into DRAM, sort them, and then throw them back to disk. And so the way this looks like on the drive is a lot of random IO, a lot of disk writes. Now, the way Mad Max works is it uses 2 temp directories, and they try to direct the majority of writes to temp 2. And so today, if you use a RAM disk or a high endurance SSD or something on temp 2 with 110 gigabytes of DRAM, then you can reduce the disk writes by, I mentioned, 72%. BladeBit is by far the fastest plotter. The fastest plot times are now just a little over 3 minutes to make a k equals 32 in Chia. And this is done completely in memory. So it does require a tremendous amount of memory. You need a high-end server or workstation that has generally 512 gigabytes of DRAM. You need 416 gigabytes is the actual amount of DRAM you need for this in-memory sort. And your performance is very dependent, obviously, the cores, number of cores, frequency of the cores, and the memory bandwidth. And so we will see scaling as we move to PCIe Gen 5, DDR5, and higher core count CPUs. We will see 20 to 30% improvement generation over generation in these plotting times as we get faster hardware. The newest one is called BladeBit Disk, and this is a very low memory requirements to start. It's about 2 gigabytes memory requirements. Of course, cross-platform and cross-OS. We work in Windows, Mac, and Linux. But the idea in BladeBit Disk is it's writing the data sequentially. So it has these map files that basically operate to keep the data sequential on disk. Now, this is really important. Sequential just means you're writing the data in the right order, LBA 0 to 100, and you're writing it in that order. And the reason why it's sequential to SSDs is interesting and important is it reduces the write amplification factor, which makes the endurance for SSDs, or the amount of data you can write to an SSD before it wears out, much greater. So BladeBit Disk was designed to take full advantage of SSD bandwidth. It's called BladeBit Disk. So as you scale more cores, you're going to need more disk bandwidth or more DRAM cache to offset that bandwidth. And so today, it has full DRAM cache support, so you can give it however much DRAM you want. If you give it about 100 gigabytes of DRAM, it does the entire temporary to sorting in memory, and so you can reduce the DRAM again by another like 70 to 75%. Sorry, reduce the disk writes by about 75%. So it's pipelined high performance CPUs, so it uses all the CPU cores and tries to do this as fast as possible. The most interesting thing about Chia plotting is it actually turns out to be a great benchmark of CPU performance, memory bandwidth, and disk performance because it is a pretty demanding and grueling workload. And in Chia, plotting is all about performance. You want to create the most amount of plots per day. And so generally, what does that mean? You want high CPU utilization. You want low I/O wait. I/O wait is when the CPU is waiting for disk. You're waiting on the storage. You're storage bound. Your CPU frequency matters because you're going to make sure you're trying to do all this sorting and in memory, and sorting is very CPU heavy, and so you need high memory frequency and high number of cores. And for a drive, the most important thing is sustained write bandwidth. And for blade-based disk, I mentioned kind of PCIe burst speeds, but you has to be able to sustain these burst bandwidth. You can't just have today a lot of consumer SSDs use this thing called SLC caching, or single level cell caching, where it caches a lot of hot writes to faster media and then offloads those when the drive is idle. Well, in Chia, that idle time never comes because you're just continually writing data. So consumer SSDs that have these write caches that are designed for these bursty type workloads generally don't perform very well. Now, the type of hardware used in Chia plotting can be a server, a workstation, or a desktop. You can generally a 8-core desktop with a standard NVMe drive and 16 or 32 gigabytes of DRAM will produce a plot in, say, 30 to 45 minutes. A workstation can produce a plot in 15 to 30 minutes. And I mentioned with high DRAM servers, you can produce a plot in 5 to 10 minutes. And so it obviously, there's no right way to do it. There's lots of people using all combinations of all these to do plotting. There is no single right way to do plotting. We've also partnered with Akash to make some of these super high-end workstations and servers that have lots of DRAM for Blaybit available to other people, so they can just buy the plots from other folks that have this equipment that are running. And this is we like to use Akash because they're fully decentralized, and you don't have to pay egress to download the plots. You are moving a tremendous amount of data. So if you're downloading plots from these plotting as a service providers, you actually need quite a bit of internet bandwidth to do that. How does farming work? A farmer is going to receive a challenge from the verifiable delay function. The farmer is going to send this signage point, the challenge, through the signage point to the harvester. And the signage point in Chia happens every 9 seconds or so. The harvester is going to take the SHA-256 of the plot ID. Each plot has its own plot ID. That's the way to define and identify a plot. It's going to hash that with the challenge hash and the signage point hash. And after you do the SHA-256 of that, there's going to be a certain number of trailing zeros. And the filter and the constant that we have set in Chia is a 1 in 512 chance. What does this mean? That means every single plot, every signage point, which again is every 9 seconds, has a 1 in 512 chance of being accessed. Now, if it passes the plot filter, then the harvester goes and does this thing called a proof quality check. A proof quality check is you're basically reading a couple tables and hashing them together to see if they make this mathematical proof and if they meet a certain matching criteria. And this is very lightweight on drives. And again, because of this filter, you're reducing the I/O by a factor of 1 in 512. You're significantly reducing the I/O to the disks. So we like to show you that farming takes almost no disk utilization, just a few 0.5 IOPS, less than that actually in practice, so just a few kilobytes per second. And most of the time it's doing this proof quality checks. If you do a proof quality check and you meet the required iterations from the difficulty, remember difficulty is how hard the blockchain is, meaning how much storage space is on the network you're competing against. If you meet a proof quality check that meets the difficulty, then you get to actually fetch the full proof of space, which is 64 random reads, and you fetch that from disk and return that to the full node to propagate out and try to make the next block in the blockchain. If you are lucky enough to get a transaction block, then you can make the transactions as well. But then if you actually have a proof that meets the difficulty in that subslot, then you actually win the rewards. And you have about 30 seconds to do this. I believe every 3 or so signage points is kind of the idea where you have to get this. So the entire end-to-end latency between when the farmer receives a signage point from the full node, you have about 30 seconds to do this whole stack. And so generally, we have some warnings in the harvester code that if this whole process takes over 15 seconds, then something's kind of wrong with your disks, like you're writing to the disks or you're trying to access them, or there's some disks that are bad or they're slowing this harvester code down. But you generally, on a regular disk, this only takes a few milliseconds. So it's not generally, one seek on our modern hard drive is like 4 to 5 milliseconds. So you can imagine doing 8 random reads or 64 random reads for full proof of space is like less than 1 second. So this should be no problem to get this to the network in time. Now, if you're in a pool, the farmer has to prove to the pool that they're actually indeed storing as much space as they say they are. The way that they do this is called a partial proof of space. Now, a partial proof of space is really just a full proof of space, but instead of sending this to the network to basically win a block, the pool is actually creating their own difficulty and sending requests to the farmers, and the farmers can respond with their full proofs of space to the pool operators and prove that they're actually storing as much space as they say that they are. And this is really interesting because the pool can adjust the difficulty dynamically to how big the farmers are. There's some pools that you do this by yourself. You can pick your own difficulty. Most of the pools just adjust this dynamically to be able to estimate how much capacity you have in a given day to a reasonable amount of accuracy. In Chia, the farming hardware people are using are generally ways to store a large amount of capacity in a small amount of space at a very low amount of power. So people are using JBODs, just a bunch of disks. This is a way to store a large amount of drives in a small amount of space in an enterprise server rack. In NAS, basically the NASs are designed to be low power, have a large amount of drives in a small amount of space. They're designed for generally home use. There are NASs that are designed for enterprise use, but NASs generally have a small amount of compute in there, and they're accessed over the network, where a JBOD is accessed directly. They call this DAS, or direct access to storage. People are putting hard drives in their desktop. Again, you can just plug in an external USB to your desktop. You can plug in the SATA hard drive. People are using desktops, and people are using lots of DIY, like Raspberry Pis with USB to connect the drives. But again, the idea there is no right way to do farming. People can get good efficiency, power efficiency on farming from one drive on a Raspberry Pi. They can get good power efficiency with a few drives on a desktop, and you can get very good power efficiency if you're scaling to tens to hundreds of drives in JBODs and racks. But generally, the Chia has better economies of scale at smaller side, which is, it's not like other cryptos. Generally, you get an advantage in Chia by having the lowest amount of power on top of the hard drive. So there's lots of ways to do this in Chia. In Chia, the drives are mostly idle, but they're accessed pretty frequently because of that signage point constant I mentioned, which is around 9 seconds. Even though most of the plots aren't accessed every signage point, because each one has a 1 in 512 chance, well, there's a pretty good chance that after multiple signage points that you're going to have at least one plot that passes the filter. And you can see here this probability percentage. If you have, say, for instance, a 12 terabyte drive and with k equals 32, every minute or so you'll have a 75% chance that the disk will be accessed. So even though this IO filter, this plot filter reduces the IO by a factor of 512, after a minute or two, the disk is always going to be accessed. So what this looks like is 99.75% idle time on the drive. As you can see, this snapshot I have in Grafana is called time spent doing IOs. That's the inverse of drive utilization. So a drive utilization, the inverse of idle time. So time spent doing IOs is drive utilization. So the inverse of that is idle time. So you can see here the average drives are only being accessed 0.25% of the time. And so the drive just basically sits there mostly idle. And in Chia, the farming goals are to basically you get rewarded by the proportional to the amount of space that you have on the network. So that's all that matters. All the extra overhead and speed of the storage and all that stuff doesn't really matter as long as you're meeting the network requirements, which I mentioned is getting a full proof of space in before the 30 seconds or so, which again, it's around 3 signage points. So in all that matters is storage density. So you want a large number of drives in a small amount of space. And generally in Chia, a way to do this is to use large capacity drives. What is a large capacity drive? I would say today with modern standards, with the highest capacity drives being 22 terabytes, today on the market for conventional magnetic recording. I'd say high capacity drive is anything like 14 terabytes and up. And you want to minimize capex. So you obviously, because the majority of cost in farming is actually the cost of the drives themselves, because they actually don't take very much power to operate. Remember, a hard drive today is between 3 and 5 watts to operate idle, and that's not very much power. So the majority of the cost in Chia farming is actually the upfront cost of the drives themselves. So a way to reduce this is to buy used drives, buy recertified drives, buy renewed drives, anything you can to leverage underutilized storage. The cheapest storage is storage that people already own. So if people already have the storage and they can use it for farming Chia, then that's going to have a lower marginal cost to them. Now, if they can minimize the power consumption of the supporting infrastructure, like the farmer and harvester, then that's better for the rewards, because remember, the total power is the power of all the equipment used to do farming. So ideally, you want to just reduce all the power consumption from all the supporting equipment as low as possible, because the drives are just going to be sitting there basically idle, and so you have to do a good job of reducing the power and everything else. Now, a nice to have is, you want to keep the drives cool so that they're not dying. But this is completely optional in Chia, right? People can do whatever they want in farming. Again, all that matters in the rewards is the storage density. I mentioned there's some quality of life stuff like having hot swap. JBODs are not great for having in your house because they're super loud. NAS is really nice because it's low power, quiet, and has hot swap drives, but they're more expensive. So there's lots of trade-offs that you have to look at between farming, and again, there's no right way to do farming. Now, if you look at the total cost of ownership in Chia for the power consumption, you would sum up the power of the farmers and harvesters, and obviously you have to plot, and there's a one-time power to plot, but generally plotting is very efficient. I mentioned the most efficient plotters today that can do a plot in, say, 3 to 5 minutes are looking at using about 0.3 to 0.5 kilowatt hours per terabyte of plots. So plotting actually doesn't consumes less than 1% of the power of over a 5-year TCO for farming. So most of the power is consumed just running the drives for farming. But you have to also, there's going to be a farmer or a harvester, and so that has obviously just a CPU, DRAM, boot drive, HBA. The specs on a harvester are very low, so you can basically have like a couple cores, 16 gigs of RAM, totally fine for a harvester. A lot of people do it with even 4 gigs of RAM, but if you're using a lot of drives, you're going to need something like 16 gigs. Now, obviously the power of the JBOD or the NAS or whatever, it's going to include expanders and fans and power supplies. But really, the majority of the power for Chia farming should be spent on the drives. And the way that we calculate this is the drives today spend most of their time on idle A because they're getting access pretty frequently. Today on a 7200 RPM drive, this ends up being about 5.6 watts per drive. And then, of course, if you're looking at the total cost of ownership, you would sum up, you may have one switch or router for a whole rack, and then you have a rack and any power cooling cost. Typically, this doesn't go into a CapEx, this goes into an OpEx, this cooling and efficiency cost for actually running the storage in a data center. But if you want to be competitive in Chia farming, you really want to reduce the power of this as much as you can to where most of the power is coming from the drives. And if you look at, I mentioned, there is not one way to do Chia farming. There are ways to do it through through desktops. There's ways to do it through enterprise. You can see here if you have like really small capacity drives, like a 3 terabyte drive, the cost may be super cheap per terabyte, but you have to use a lot more of them, and so the power for all that equipment is increased. We call this total cost of ownership, and you can see here, used 8 terabytes, 18 terabytes new, used 12 terabytes. These are all very good and competitive TCO if you can do it right with the right balance of equipment. So there is no one way to do Chia farming. Now, obviously, I'm going to say the most competitive Chia farmer is one that gets their storage for free or has some competitive advantage, like they have their plotting for free or have power for free. There's lots of people that have one or two competitive advantages, but it would be very, very rare to see somebody that has more than one of these major advantages. But again, you can, and this is all very basic and easy. We have a model on chiacalculator.com/RY that basically goes through this TCO model. There's also a video I did there that I'll elaborate on that goes through the rest of the Chia total cost of ownership and how you would calculate this by yourself. So with that, Hope that was interesting and learned a little bit about plotting, farming, and how some of the proofs of space on Chia work. Again, this is very exciting stuff, and we have follow-up videos on Chia power consumption, deep dives on a lot of these topics on my own channel. So with that, thank you guys. Bye-bye.